Hello, my name is João Fidalgo and I am an engineering physics master student from IST. This video will focus on the theme of my master thesis, Sub-100nm Spintronic devices on large area wafers. The work will be oriented by Professors Susana Freitas and da Silva and will be developed at INASCAMien. In a rapidly evolving world, information is generated faster than ever. It has never been as important to figure out how to store all this information faster and in smaller areas. Data storage alternatives are therefore increasingly important to explore. Although online cloud data storage is a good alternative with increasing hold, safer alternatives resorting to physical storage methods must also be researched. Competitive storage alternatives should not only be smaller, but also consume low power, have high endurance, operate fast and be non-volatile. This means that information is stored without the need for a power supply. Many different types of devices are already available, such as flash drives, hard disk drives, solid-state drives or random access memories. We will focus on a spintronic device called a magnetic tunnel junction, to be used in a magnetoresistive random access memory architecture. A magnetic tunnel junction consists in two layers of magnetic material, with a thin electrically insulating layer in between. The junctions are typically very small, with dimensions on the order of hundreds of nanometers. The insulating layer may be as thin as a few layers of atoms. One of the magnetic layer's magnetization is fixed and is called the reference layer, while the other has a free magnetization and is called the free layer. Note that in this case the magnetizations lie preferably in the direction perpendicular to the plane of the device. The fact that a given direction is more favorable magnetically than another is denominated of magnetic anisotropy, which in this case is called perpendicular. The magnetization of the free layer will prefer to lie either parallel or anti-parallel to the magnetization of the reference layer. These two states can then be interpreted as a 1 or a 0, effectively representing a bit of information. If a current is applied through the junction, the electrons may pass through the thin insulating barrier by tunneling effect. If the magnetization of the free layer is aligned with that of the reference layer, then the electrons will tunnel through the barrier more easily, leading to a lower electrical resistance. If the magnetization lies in the opposite direction, then the resistance is higher. This is called the tunneling magnetoresistive effect, and it is used to read the state of the device. The writing operation is typically done by applying a magnetic field in the parallel or anti-parallel direction. This is done using auxiliary current lines, around which a magnetic field is formed. The magnetization will align with the applied field if it is strong enough. However, this mechanism requires high applied power. An alternative method consists in switching the magnetization by applied current. The magnetization of a given magnetic material corresponds to a majority of electron spins pointing in a given direction. This is called spin polarization. Therefore, when a current is applied, the conduction electrons also become spin polarized, according to the direction of the polarization of the magnetic layer they cross. The effect of this current polarization is an applied torque on the free layer magnetization, and is called spin transfer torque. If the electrons flow from the reference layer to the free layer, then the electrons that pass through to the free layer have their spin aligned with the reference, and apply a torque to align the magnetization with it. This process requires lower switching currents, and therefore needs less operational power. The electrodes used for reading can also be used for writing, facilitating integration. In summary, my thesis work consists in demonstrating current-induced switching in magnetic tunnel junctions with perpendicular magnetic anisotropy. Follow my work and see the development of the future of physical data storage. Thank you for your attention.